Alright, welcome back guys. AP Chem Chapter 11. We're going to go ahead and finish up this set of chapter notes here. This is where we left off last time. There's this image of a X-ray tube firing a beam through a crystal, and then the crystal is deflecting these beams onto this plate. And then what we're going to do with that is we can measure the lines on the plate, these reflected rays, and we can determine from that the incident rays. And like math people frequently do, they make a whole bunch of triangles out of everything, and they can figure out about how far one particle in the crystal is from another particle in the crystal. So it's kind of a cool thing. They determine this extra distance here between points B and C and D. And so we get this formula. It's called the Bragg equation. 2d sine theta equals n, which is the principal quantum number, times the wavelength. So here's an example of how you could do a problem like that. X-rays, they give you the wavelength, are diffracted from a crystal at an angle of 14.17. If n equals 1, what's the distance in picometers between the layers of the crystal? So you use your Bragg equation. You say n equals 1. We have our theta of 14.17. And our wavelength, we change from nanometers to picometers. We solve for d. And that's all there is to it. 314 picometers is the distance between layers in a crystal. So, types of crystals. There's ionic crystals. That's lattice points occupied by cations and anions. They're held together by the electrostatic attraction of the cations always being positive and the anions always being negative. They're going to be like ionic compounds, hard, brittle, pretty high melting points, pretty poor conductors of heat and electricity, at least in the solid state. So there's cesium chloride, zinc sulfide, calcium fluoride, and all of their different crystal formations. Then there's covalent crystals, another type of crystal. We have atoms that are held together by covalent bonds. That makes them covalent. These are going to be pretty hard crystals with a pretty high melting point. Again, poor conductors of heat and electricity. Diamond is one example of a covalent crystal of just carbon. And then graphite is another covalent crystal of just carbon. And of course, diamond is, you're familiar with the very hard rocks and rings, and graphite is actually the lead in lead pencils. When you write with lead pencil, you're scraping off these individual layers of carbon onto paper. So then there's molecular crystals, which means we have molecules at each lattice point. They're going to be held together by IMFs, or intermolecular forces. They're going to be pretty soft crystals with a pretty low melting point. Again, still poor conductors of heat and electricity. And their example of that is benzene. Benzene crystals are made of individual benzene molecules, and of course water crystals or ice is made of water molecules bonded to other water molecules. So then there's metallic crystals, where of course all of our lattice points are occupied by metals. They're held together by metallic bonds. Some metals are pretty soft, some metals are really hard. Some melt at really low melting points, others are very high. They're good conductors of heat and electricity. And here's an example of how a metallic crystal could look. All of the metal atoms are positive. They're surrounded by a sea of electrons. That's what makes them such good electricity conductors. So the nucleus is on the inside, and the sea of electrons is kind of moving all over around the outside of those positive nuclei. So here's just kind of an overview of what we just talked about, the differences between the types of crystals: ionic, covalent, molecular, and metallic. Now there's an amorphous solid, which is a place where we don't get these well-defined arrangement of molecular order. Glass is optically transparent fusion. From inorganic materials, it's cooled to a rigid state, but it's cooled without crystallizing. So glass is an amorphous solid. So there's crystallized quartz, silicon dioxide, and non-crystallized quartz glass. And so difference between quartz and quartz glass, you can see the molecular structure here is really pretty random. And here it's very linear and logical and well organized. And so there's a difference between a solid and a glass. So high temperature superconductors, Here's the example of molecules at really high temps acting kind of odd, or really low temps acting kind of odd. The superconductors, they can conduct something through space pretty much without friction, or repel magnets, without friction, and we can use these for transportation and all sorts of things. So that's kind of a cool deal. Here's another example of the importance of chemical solids. This is an example of Napoleon and his army invading Russia, where during the winter it was, of course, incredibly cold, and their buttons on their coats were made of tin, and most of the tin that we see is white tin, and it's a pretty strong metal, but if your temperature drops below 13 degrees and it gets very cold for very long, the white tin actually decomposes into gray tin, and gray tin is a very weak form of that metal, and it will kind of just fall apart. So the buttons on the soldiers' coats would fall apart. It'd be a lot harder to stay warm, and if you're in Russia, that's not a very good thing. So here's some examples of phase changes. Hopefully you're familiar with a lot of these. Solid, liquid to gas as you increase in temperature. If you go straight from a solid to a gas, that's sublimation, like solid carbon dioxide does. If you go from solid to a liquid, that's melting, like ice cubes. Liquid to a gas is vaporization. To become a vapor is to evaporate. If you go liquid back to a solid, you're freezing. If you go gas back to a liquid, you're condensing. And then if you go gas straight to a solid, that's deposition. That's what causes frost. So the greatest order would be in the solid state, and the least orderly would be in the gaseous state. So here's how temperature affects molecules. Kinetic energy, temperature 2 is going to be greater than temperature 1. And here you can see that as our kinetic energy increases with our number of molecules, our kinetic energy decreases a lot if you have fewer molecules. And at temperature 2, the higher temperature, even as we get fewer molecules, our temperature still stays really high. Our energy still stays really high because we're at a higher temperature. So being at a higher temperature is going to create a lot of energy. So equilibrium for vapor pressure is vapor pressure measured when a dynamic equilibrium exists between condensation and evaporation. So as fast as gases are becoming liquids, liquids are also becoming gases. That's equilibrium. And so here we have a glass of water sitting on a table is at equilibrium between all of the liquid water in the glass and all the water gas sitting right above that liquid. And so our dynamic equilibrium means that we have condensation rates equal to evaporation rates. And so it could look something like this. We're evaporating, we're condensing, and when we get to that point where these two are the same, then that's equilibrium. So here's the way they can measure it. Frozen liquid, there's no evaporation occurring, and we have a vacuum over here, and then as that frozen liquid becomes liquid and starts to evaporate, it pushes up this little barometer reader here. And so there's the way we know that. Molar heat of vaporization is the energy required to vaporize 1 mole of a liquid at its boiling point. Vapor pressure versus temperature, you can see as the temperature goes up, so does the vapor pressure. Here's another equation, the Clausius-Clapeyron equation. It's not something we're going to use very often, but if you used it, it's natural log of P, equilibrium vapor pressure. T is temperature in Kelvin, which is what you want to default to with gases. R is the gas constant. So, few alternate forms of the equation. 2 different temperatures. You can solve it for 2 different temperatures. And there it is. Boiling point. So boiling point is a temperature at which equilibrium vapor pressure of the liquid is equal to the external pressure. And the normal boiling point is a temperature at which a liquid boils when the external pressure is 1 atmosphere. And so here's some boiling points. That tells us a lot about molecules and how strong their IMFs are and all sorts of stuff like that. So a critical temperature is the temperature above which the gas cannot be made to liquefy, no matter how great the applied pressure. The critical pressure is the minimum pressure that must be applied to bring about that liquefaction at the critical temperature. And so we can get things so hot that they can't be a liquid. No matter how much pressure we put on them, they can't become a liquid anymore. And if we get them right below that temperature, then the amount of pressure it takes to make them that liquid, that's our critical pressure. So here's kind of an example of this occurring with the temperature below the critical temperature, the temperature above the critical temperature, so we're liquid, we're gas, the temperature about the critical temperature, we've just put a ton of pressure on that, and we're trying to get it back to, a liquid, and then the temperature less than the critical temperature is we're kind of back to that liquid state again with a little bit of gas above. So solid-liquid equilibrium, melting and freezing. Melting point of a solid or the freezing point of a liquid, either way, is the temperature at which the solid and liquid phase coexist in equilibrium. This is the reason that when you drop a couple of ice cubes in a glass of water, the ice cubes stick together because they are freezing the water in between them, and they're also melting in the water at the same time, and so they're kind of creating a little bit of water in between each ice cube and then freezing it themselves, so they stick together. So that's melting and freezing. Molar heat of fusion is the energy required to melt 1 mole of a solid substance at its freezing point. And so here's another chart comparing melting points and how that relates to their delta H of fusion. Here's a heating curve or warming curve. As you move from solid to liquid to vapor, the easy trend to see is that we're increasing in temperature. The less obvious trend is that at the point where we're not all solid and we're not all liquid, our temperature actually levels out. There's no temperature change at what's called a phase change. And between liquid and vapor, there's no temperature change at that phase change either. Solid-gas equilibrium. The molar heat of sublimation is the energy required to sublime a mole of a solid. And so the heat of sublimation is equal to fusion plus vaporization. So to go straight from, a solid to a gas, we can add up the heats from solid to liquid plus liquid to gas. Kind of makes sense. That's Hess's law, of course, taking separate steps and adding them up to the overall step. So there's sublimation and deposition on our graph from earlier. So a phase diagram is what we use to summarize basically when it's a solid, when it's a liquid, and when it's a gas. Here's water, and we can see our temperatures down here, 0 degrees Celsius. We're normally used to water freezing because we exist at 1 atmosphere or a little less, so we're used to about right in here. If it's very, very cold outside, if the water is very, very hot, it goes from about liquid water, we're used to boiling water, which is the vapor phase. And so we can see that if we were to change the pressure, we could actually make this look a little bit different. Go straight from a solid to a vapor. Or if we made the temperature very cold, we could go straight from a vapor to a solid. Things like that. Then carbon dioxide, you'll notice the graph's a little bit different. Pressures are different, temperature ranges are different, but the idea is still the same. Solids on the top, liquids on the top, vapors on the bottom, kind of like water back here. So, because we exist at 1 atmosphere, you and I rarely see carbon dioxide as a liquid. I can show you how we can do it, but generally we see solid CO2, dry ice at the grocery store, go straight to the vapor phase as it warms, and we never see liquid because liquid exists at like 5 atmospheres, so it's pretty high up here. And you can create that in a lab, but for what most of us see, solid to vapor, and there's dry ice becoming a gas, subliming. So, effects of increase in pressure on the melting point of ice and the boiling point of water. And so here, if you change your pressure, you're going to change your melting point and your boiling point. So if you increase the pressure up to here, your melting point temperature is going to be a little bit higher. Your boiling point temperature is going to be just a little bit higher. And if you lower the temperature, you're going to lower the boiling point, that kind of stuff. So then here's our last slide. Ice skating. Ice can change its phase with more pressure. If we have ice here at 0 degrees Celsius, in the solid phase, and we add a bunch of pressure through our tiny blades of an ice skate, our pressure comes up here. And what it does is it makes our ice become a liquid. And so because of the pressure from the skater's ice skates, she is going to melt that ice as she skates on it, just a little. And then it refreezes if it's cold when she's not skating on it anymore. But over time, of course, that can make the ice pretty wobbly and uneven, and so ice skaters want pretty smooth ice, and that's the reason they have to bring those big machines over the ice in between like hockey games and all that kind of stuff, because as a person skates, they actually melt the ice they skate on because of the increased pressure. And with that, that's the end of chapter 11.